Myself, Sanjay Kumar Sonker. I am assistant professor in AKGE Kumar Engineering College. In this lecture, we discuss about the asymptotic notations in a design and analysis of algorithms. Now, come to the asymptotic notation. Now we discuss the asymptotic notation. Basically, asymptotic notation is the abstract notations for describing the behavior of a functions and in terms of the rate growth of a functions. We just observe it. It's also a mathematical way to representing the time complexity of any given algorithms in terms of times and memory space, memory complexity. That is a growth of function. Now we discuss about the types of asymptotic notations. That is three types of asymptotic notation is. First is defined as a big O notation. Second one is a big omega. Omega notation. Third one is a theta notation, defined as theta. Now, before we discuss this classification of asymptotic notation, we just take an example to understand the asymptotic notations, how it's work. Now, we just take an example. If I am a developer, you are developing the algorithms, you come to me and I give you enough time to develop algorithms. I know that this algorithm, just take example, algorithm A1, it's taken, maybe it's taken 1 month, but I give you 1 year to develop these algorithms. Okay, the cost is 1 year. I give you 1 year, but actually this algorithm is taken 1 month. That's known as a big O notations. I give you 1 week, but it's taken more time to develop this algorithm. Is maybe take a 1 month, 2 month, and so on. That is a less. It's known as a omega notation. It's known as a omega notations. Next is a theta. That's the theta is defined as the exact time. That is a good for any client. Okay. Now, this is not as exact. I'm just taking this is algorithm. A1 algorithm is exactly developed in 2 days. I give you 2 days to develop these algorithms. This means it's not as a theta notations. I'm just take example. Another example, you just easily understand. एज्यूम करिए कि मेरे पास आते मैं आपको एक कॉस्ट दे देता हूं कि मान लीजिए कि किसी भी एल्गोरिथम को डेवलप करने के लिए मुझे एक कॉस्ट की जरूरत पड़ती है, जैसे मैं दे देता हूं आपको टाइम। मैंने मान लीजिए आपके पास एक एल्गोरिथम है, आप मेरे पास आए डेवलप करने के लिए, मैंने आपको मैक्सिमम टाइम बता दिया कि इससे डेवलप है, मैक्सिमम टाइम इज ए 1 ईयर। इट्स नॉट एज ए बिग O notation. It's known as a big O notation. It's known as a big O notation. Is it? Next is it? Maybe हो सकता है मैं आपको क्या बोलूंगा कि it's take a less time. I give you 1 week. You meet me 1 week, and another 2nd week, and again we extend this time is 3rd week. Okay, this is mean is a omega notation. Theta notation is defined as a exact time and give you exact time to complete the algorithm. This is very good for any developers, but it's not a possible. It's a only possible is a big notation. Big omega notation is a possible, not possible to this one, and this one is not be possible. Most popularly we are using to the big O notations. Now we discuss the big O notation. Big O notation. Now we just take a graph along with time complexity, that is a time. It's a number of inputs, that is a n. We just take a 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. That's the inputs. We just check the behavior of a true positive function. We just take a true positive function f of n and g of n. Is it true positive function? Okay, there is a true positive function. We just check the behavior of f of n and g of n. Now we just observe this behavior. At we cannot be observe the behavior in a less inputs. We just observe the behavior in as possible as inputs. We are just to check the behavior is a large inputs. Now we just take a n naught here. Observe the n naught. This is a constant. That is a C1 of g of n. Now, function f of n is changing the behavior in a less inputs, and after this inputs on a large inputs, the behavior is a fixed. Behavior is fixed. This behavior is a fixed f of n. Now we just take the asymptotically equation is f of n is less than and equal to f of n is defined as a f of n is defined as a big O of g of n. This inequality we discussed the mathematically, that is a f of n is asymptotically is less than and equal to constant c dot g of n. Okay. Now we just check for r value of n. N is greater than n naught such that 2 positive constant c and n naught, c is greater than 0 and n naught is greater than 1, greater than or equal to 1. That's a statement of a big O notations. Now we just check this mathematical expression with the help of example. Now we just take example. F of n equal to n square plus n plus 10. G of n is given as a n square. We just check this inequality of mathematical. F of n square plus n plus 10 equal to constant c dot n square. We just check here. Now observe this function. We just take a constant. If we increase this constant, that is a greater than n and equal to the f of n. We just take a value of c. We just calculate the value of c. C is just calculated as the maximum value reached for n square is n square. N value reached to n square. 10 is also reached to n square. That is a maximum. That is a 3n square. Now the constant is c equal to 3. We just take a c equal to 3. Observe it. Value n square plus n plus 10 is less than n equal to 3 n square. I'm just write this here. 2 positive constant. Now here is n square plus n plus 10 is less than and equal to 3, n square, observe it, c equal to 3, and next we find the value of a next constant n naught is given here. We just apply the n equal to 1, it satisfies the equation. First is just check it, 1, 1 and 10, that is a 12, 12 is less than equal to 3 into 3, that's not satisfied the equation. N equal to 2, we just check it, 4 plus 2 plus 10 is a 16, it's not satisfied the equation. Next we just take a n equal to 3, just observe it, n equal to 3, 3 square plus 3 plus 10 is less than equal to 3 into 3 square, observe it, 9 plus 3 plus 10 is less than equal to 3 into 9, 19, 22 is less than and equal to 27, that's if greater than, 27 is greater than this function. So value will be n naught will be start from n equal to 3. It's a not check the behavior. Now next we discuss about to the big O notation, big omega notation, defined as a big omega. Okay, now we just draw the diagram. That's a time along with time and number of inputs, 1, 2, 3, 4 and 5, 1, 2, 3, 4 and 5. Observe it, we just check the behavior in n naught. There is a behavior is changes, function behavior change. Here function behavior is not change, function not see a change. So we observe that the behavior, that is a constant c g of n function. We are just take a two positive function, f of n and g of n, that is a two positive function. Next, now we just take a f of n, we just take another color, f of n. Here the f of n function behavior will be changed, sometimes is up and sometimes is down, but after the n naught the behavior is not change, that is a f of n. Okay, now observe it. Now just take a statement, f of n is equal to omega of g of n, means f of n, mathematically f of n is greater than and equal to c g of n. C is a constant, where c is a constant. For r value of n, n is greater than and equal to n naught, maybe n naught, and such that two positive constant c is greater than 0 and n naught is greater than equal to 1. That is a mathematical expression for this function. Now we are check this asymptotically mathematically expression with the help of example. Understand, with example. Now we just take example here. We are using to f of n equal to n square, g of n equal to n square plus 10. Now we observe that f of n is equal to omega of g of n, we just check it mathematically. F of n is greater than equal to constant g of n. Now here we calculate the value of c and n naught for the function of f of n. Now just check it. N square is greater than or equal to c dot n square plus 10. Now how this function is less? We just take a value of 1, is not be less. So we just take a value of, if we taking a 1, c equal to 1, it's not a less than, it's equal but not less than. Okay. Now we just check a c equal to 1 by 2. Yes, 1 in a c equal to 1 by 2. This g of n is a less than f of n. So observe it, c equal to n square is greater than equal to half of n square plus 10. Okay. Now we solve its inequality. N square is greater than n equal to n square by 2 plus 5. Observe it. Now come here. We just continue here. N square minus n square by 2 is greater than equal to 5. That's it. N square by 2 is greater than equal to 5. N square is greater than equal to 10. Okay. The value of n square is greater than equal to root 10. Now we calculate the value of a root 10 is come to 3 point, near about to 3 point. N square is always greater than equal to n. N is greater than, okay, here. N is greater than n equal to 3.14 something. You just calculate the value of a root. N is greater than and equal to near about 4. Now we just take a value n equal to 4. For a n equal to 4, it satisfied the equality, this asymptotic notations. Now we just take a value of n equal to 4. Just put the value of n equal to 4. Observe it. N equal to 4, f of n is greater than equal to c dot g of n. We just check it. N square is greater than equal to 1 by 2 n square plus 10. Observe it. Now here check f of n. Observe it. N square is greater than and equal to n square plus 10. Constant c. We just calculate the value of c equal to 1 by 2 and n equal to 4. Put this value here. 4 square is greater than equal to 1 by 2. 4 square plus 10. That is 16 is always greater than equal to 16 by 2 plus 5. 16 is always greater than equal to 16 by 2 plus 5. That is a value. Value is start from n equal to 4 is, okay, from 4, 5, 6 and so on. We just observe the behavior of a function f of n in a input of 4. That is a omega notation. Now we discuss about to the theta notation. Theta notation denoted as a theta. Now observe this diagram. Time and inputs 1, 2, 3, 4, 5, 1, 2, 3, 4 and 5. Now we observe it in input of n naught equal to 4. We check the behavior. That's a constant. We just reach the constant, and another is a C1 g of n, C2 g of n. Okay, now we check the function behavior. Observe it function. Within 4, behavior will be changed. Within 4, f of n behavior is a f of n behavior will be changed. After this 4 and not value, the behavior will be same, f of n. Now we just check the function. F of n is less than and equal to C1 g of n, or f of n is greater than and equal to C2 g of n. This is denoted as a theta notation. Now observe it. For a r value of a, for r value of a n, n is greater than n naught, n is greater than and equal to n naught, such that 3 positive constant C1 and C2 is greater than 0 and n naught is greater than equal to 1. Okay, now observe here is, in this case we just define as a f of n equal to theta of g of n. Now we observe it. Same is for our value of, it's a f of n is less than and equal to C1 g of n, and another is a first case first, that's a case second, f of n is greater than and equal to C2 g of n. This is defined as a, both cases here. Observe it. For r value of a, see, r value of a n, n is greater than and equal to n naught, and there is a 3 positive constant C1, C2 and n naught. C1, C2 is greater than 0 and n naught is greater than equal to 1. It's defined as a theta notations. Now we just take an example to easily understand this inequality with the help of example. Now we just take example. We just take a function f of n equal to n square plus n plus 10, and g of n is given as a n square. Okay, observe it. First we just check, complete this notation and this notation. Now we observe it, the value. Observe the value, f of n, n square plus n plus 10 is less than or equal to constant C1 n square. We just calculate the value of C1, and n naught. Now observe here, we just calculate the value. Is RV is greater than this function, we just take a value 3, is RV is greater than n square plus n plus 10 less than or equal to 3 n square. We start the value of n naught is 1, 2. In a 1 and 2, it's not, behavior will be changed for the f of n. Behavior changing, but but after 2 with value n not equal to 3, behavior will be same, not be changed after n equal to 3. We just put the value of n equal to 3, 9 plus 3 plus 10, 22 is less than equal to 3 into 9, or 22 is less than equal to 27. We just check a value of n not equal to 3, 4, 5, 6. It will be growth of function, will be growth, always growth. Okay. Next, we check the another cases. Case second, n square plus n plus 10 is greater than equal to c2 n square. Now we just take a value of c2 n square. We just use this value c. We just take a value c. If we put the value of c, c2 equal to 1, it satisfied the equation. Yes, n square plus n plus 10 is greater than equal to 1 n square. Yes, n square, this is reached to n square, this n is also reached growth to the n square, 10 is also growth with n square, maximum growth is n square, is it 3 n square. Here is a 1 n square, so 3 n square is greater than n, maybe equal to n square, depend on the constant, that is a c constant 1. Okay, now value is c2 is 1 and c1 value is 3. Now we calculate the value here. C1 is 3 and c2 value will calculated 1. Both 3 and 1 is greater than 0. It's satisfied. Now value of a n naught we calculated. Here n naught value is 3. Now here we calculated n naught value is, we just put the value of n naught is 1. We just check the value of n naught equal to 1. Is satisfied or not? 1 plus 1, 12. Just observe it. 1 square plus 1 plus 10 is it 12. 12 is greater than equal to 1. It's satisfied. We just check the value of n not equal to 2. 2, 4 plus 2, 6. 6 plus 10, 16 is greater than equal to 2 square, 4. It's satisfied. So n naught is 1, 2, 3 and so on. Okay. So n naught value will be start from 1, 2, 3, 4 and so on. Here we start with 3 and here we will be 3. So n naught value here is, n naught is 3. So we define this. Finally, we define the function f of n equal to theta of g of n. So it's a asymptotic notation is given as a theta of g of n is a theta of n square. That is a calculation. Okay. Now we discuss about the complexity of a classes. Now observe the some complexity of a classes. I'm just write the complexity. Okay. So now we stop here and continue to the next lecture with complexity of classes. Thank you.